Okay. All right, so today's lecture builds directly upon the last lecture. The topic is network flow. Right, so last class we were looking at this kind of general question of trying to identify how well connected two vertices are in a network, which has many natural applications, from infrastructure to connecting parts of a CPU to analyzing social networks, analyzing the World Wide Web, right? And of course, there's many different ways to formulate this general question, and the value may depend on the application. But out of this list, we focused in on the last two questions: the maximum number of edge disjoint paths and the minimum number of edges in an ST cut. So the edge disjoint path problem, we had a graph, and I was just trying to find paths from left to right that don't share any edges. Okay. Here the solution was 2, and it was certified by, let me talk a little more, which is also an example of a packing problem, in the sense that I'm trying to kind of pack ST paths into edges. So each path uses up all the edges it takes. The dual problem was the minimum ST cut. So here the goal is to delete as few edges as possible, so I can't go from S to T anymore in the remaining graph. Okay, here the solution was 2, which also told us that our previous solution for packing paths was optimal. Okay. So if the last problem was a packing problem, then this one can sort of be seen as a covering problem, in the sense that I can think of an edge as sort of covering any path that uses it. Okay. And with that vocabulary, the goal is to choose the minimum set of edges to quote-unquote cover all of the ST paths. Okay. So these problems are dual packing and covering problems to each other, which is one reason why we start to see all the coincidences that we see, although we directly analyze paths and cuts, because it's a little easier to think about and visualize. Okay. So we always had this underlying duality. Now we wanted to show them that the two quantities are equal, and we did it in 2 steps. First was the inequality, that the number of paths you can take is at most the number of edges in any ST cut, and this one was much more straightforward to prove. Quite simply, any edge in your cut can only cover one path at a time, because the paths are edge disjoint. Okay, but then to get equality, we instead we shifted into an algorithmic discussion. How do we actually compute a maximum packing of paths? The most natural idea is to just willy-nilly choose paths and rip them out of the graph. That will make sure that what you select is edge disjoint. Right? But this doesn't always work. So here was a simple example that we focused in on. Of course, there's 2 paths from left to right if you went, top and bottom. But if the first path you selected used that middle edge, you won't find a second path in the remaining graph. So this simple algorithm wasn't good enough. But we sort of kind of looked at the problem a little more closely, and we developed this idea of, I can kind of cancel out opposite edges. I can sort of uncross opposite edges to get 2 paths. There's no opposite edges. Okay, so we had, for example, this lemma. And that led to this augmenting path algorithm. It's very similar to the greedy algorithm, except whenever I take a path, instead of removing all the edges, I added the reverse of all the edges I selected. Okay? Because I know that in a future iteration, if I sort of take this fake, reverse edge, artificial edge, I can kind of uncross it with a previously selected path and get those two edge disjoint paths. Okay. So that was the key idea was sort of, the idea of just choosing paths wasn't so bad, but the key idea was sort of to very carefully update the graph that we keep working in. It required a little bit of structural observations. We analyzed this algorithm, the Ford-Fulkerson algorithm, the augmenting path algorithm. And to prove it was optimal, we did something interesting, which is that we looked at the residual graph at the end. At the end, S cannot reach T, because you can't find any more paths. And we looked at, say, the set of vertices that S can reach, okay, which corresponds to a set of vertices originally. And you can look at all the edges that left that set in the original input. Okay? And our proof was, every time I chose a path from S to T, the number of edges in that cut went down by 1. Because ultimately I'm just kind of sending one unit of flow, or one path from left to right, and that added a reverse edge. Okay? And so every time I add a path, the number of edges in the cut goes down. At the end, there's no edges left in the cut. So if I've taken 10 paths, I've deleted 10 edges, and the size of the cut is equal to the number of paths repacked. Okay? And when we combine that with our kind of relatively easy lemma, that the number of edges in the cut is always at least the number of disjoint paths, we end up getting equality everywhere. So not only did we get a nice algorithm, but we also got all of these nice theorems, including this fact that always the maximum number of edge disjoint S to T paths is equal to the number of edges in a minimum S to T cut. The algorithm itself, due to Ford and Fulkerson, takes linear time per path you select. So the common way to state this is to say it takes m lambda time, where lambda was the value, the optimum value. It'll give you both the path packing, and it'll give you the minimum ST cut. Okay, so I did preview last time today's discussion. And this is a very natural extension where I'm going to give capacities to all the edges. Okay, so from a path packing point of view, if an edge has capacity 3, that means I can now use that edge up to 3 times. Before, in a sense, we always had capacity 1. And now we're generalizing that to bigger values. Okay. So I think we did this last time, but so in this very simple example, we can get a solution of 5. Okay. Within the purple capacities. Okay, so the edge that's labeled 3 is appearing in 3 paths. The edge that's labeled 2 is appearing in 2 paths, and so forth. Okay. All right. So, okay. So, one thing worth pointing out, if the capacities are integers, then we can think of sort of a capacity of 3 as just having 3 copies of an edge with sort of capacity 1. A multi-graph. So we could always kind of reduce to the unweighted case by multiplying stuff. But now we run into some algorithmic problems because lambda can be really, really big. If I just multiply all the capacities by a gazillion, now lambda is the original value times a gazillion. And that wouldn't count as a polynomial running time anymore. And that's only the clean case when the capacities are integral. But it's totally natural to say, oh, the capacity the edge has capacity of 1.3 or 1.9 or something, or pi. Doesn't have to be a rational value. So we might start thinking about, okay, maybe I can't pack paths in integral units, 1, 2, 3, but I can't take 0.1 of a path, 0.2 of a path, and so forth. And so I can consider this sort of fractional version of the problem where I'm kind of coming up with a weighted combination of paths. Okay. So let me go through this a little bit slowly. Okay, so when we're talking about path packings with capacities at some level, especially if lambda is big, I don't want to like save a copy of a path for every unit of lambda. So I'm going to be instead thinking about constructing weighted combinations of ST paths. Okay, so maybe I would write PST to be sort of the family. This is just kind of setting up some notation of all ST paths. This is an exponentially large family. That's okay. We're not necessarily writing out all the paths. Okay, this is more sort of conceptual. Okay, so I might define a path packing as sort of like a set of weights, probably mostly 0, but I'm thinking I assign non-negative weights, a non-negative combination of S to T paths. So it could be 0.1 of this one, 0.2 of that one, 0.3 of the next one, and 0 for the rest. Probably you'll just have a small set of paths in your combination. Everything else is by default 0. And to sort of write out the capacity constraint sort of cleanly, I think probably will agree with everyone's intuition, but we might write for all edges E. If I sum up over all the paths from S to T, the paths that contain that edge E, okay, and then whatever quantity I take of that path, so x sub p could be 0.5 if I'm taking half a unit of this path, I want all of this to add up to at most the capacity of the edge. Okay, so this should be sort of entirely in line with the earlier description, just made a little bit more boring by writing out the mathematical inequality. Okay. All right. So this is still kind of in a sense a packing problem. It's just the suitcase is a variable size. Different edges can have more paths running through it. Okay. I should have allocated some space for this. At the same time, we can also talk about capacitated cuts. Okay, so before we were just interested in the number of edges in any ST cut. Right, which is sort of very natural. Now, if we're going to continue with our analogy where like capacity of 5 is equivalent to 5 copies of an unweighted edge, then instead of counting the number of edges in our cut, we should be interested in the total capacity of the cut. Okay? So, if I'm given some set of edges C, this is just summing up the capacity of the cut. Okay? So now when I say I'm looking for the minimum ST cut, I really mean I'm looking for the minimum capacity ST cut. That is the quantity that actually limits the total amount of paths I can pack. Okay. All right, so let's walk through slowly something that at some level we've already kind of discussed more briefly, more quickly. If I look at integer capacities, then at some level the path packing problem, trying to pack as many paths as possible, is equivalent to that unweighted problem where I just duplicate edges. And then the minimum capacitated cut problem is equivalent to the unweighted problem where I just duplicate the edge however many times. Okay. So we can reduce this. This is not algorithmic. We're only worried about reestablishing some of these equalities. We can reduce to the kind of edge disjoint case. Okay, we can reduce to the edge disjoint case. And again, we'll still get that the max number of paths is equal to the min cut for integer capacities as well, where now max paths is referring to kind of like the total quantity, the sum of x's, and min cut is referring to the minimum capacity over any ST cut. Okay. Now, eventually I want to work my way up to real valued capacities. The next step is rational capacities, right? So this is when the capacity of an edge is like, I don't know, 33 over 100 or something for various edges. Okay. But as I asked you guys last time, and it was answered by the class, we can clear denominators. Okay, so in this case, I can multiply everything by 100 or something. If I clear denominators and multiply it by a big integer, I'm left with integer capacities. In that integer problem, this max pass is equal to the min cut. And then when I divide everything down, we still have max pass is equal to min cut. Okay? So just by scaling up and down, we reestablish this very nice thing. Okay. All right. Now the weirdest case. The weirdest case is when we have real capacities. Maybe right? The capacity of the edge is equal to pi or something. Maybe it's equal to square root 2. It's not obvious that you can just clear denominators and reduce to integers. Okay. Nonetheless, I want to be very lazy. So, one thing that we can do is we can make a new set of capacities that are rational, but very close in value to CE. Right? So, for example, if I define a new set, I'll call it C tilde. And it was very close in value, like I write 3.14 or something. Okay. Then, of course, the difference between the two capacities is something small. 159, whatever. Okay? So in general, we can choose some small epsilon greater than 0 and pick rational capacities. So that the difference is at most epsilon. Okay, you can always take any real number and approximate it sufficiently close with a rational number. Okay. And what that'll give us is sort of like for the rational capacities from what we previously did, I'll write like max pass with a tilde above it. For the rational capacities, I know that max pass is equal to the min cut. Okay. And what that tells us, okay, so if I, maybe I've increased the capacity of every edge by some amount epsilon, so I can only pack, m times epsilon more paths or something. Okay. And likewise, maybe I've decreased the capacity of every edge by at most epsilon, so the total minimum cut has gone down by at most m times epsilon or something. So what that tells me is that with respect to the original capacities, the real valued capacities for which we don't yet have a theorem, okay, this value is at most epsilon times m, or maybe 2 times epsilon times m or something. M just because every edge has changed by epsilon. Okay. But epsilon I can make arbitrarily small. So as I send epsilon down to 0, then the two values have to be equal. Right, what we've shown is that the difference is less than any finite value. That means they're equal. Okay, so not too interesting. All we've done is sort of reestablish that also for real valued capacities, we have all this nice maximum number of paths or maximum quantity of paths you can pack is still equal to the minimum capacitated ST cut. And it's not really a big deal if they're real valued capacities or rational or integer or whatever, as far as the mathematics are concerned. So all that's left is the algorithmic issue of how am I going to make an algorithm that works for capacities. Obviously, clearing denominator is going to make lambda really big and stuff like that. And this kind of approximating, introducing some epsilon and sort of rounding the real value capacities and plugging that into our existing algorithm will only give me approximate solutions. They'll always be off by epsilon. So I want to deal with this issue of sort of the scaling, getting rid of this lambda issue, and 2, also kind of doing things very exactly. Okay, so we'll need some stronger arguments. Okay. But I want to present that algorithm in the context of a closely related problem called max flow, okay, which is going to be just like our path packing problem, except at some level, I'm not even going to be worried about the path part anymore. Let me explain. Okay, so your input is still a directed graph with capacities and a source and a sink. Okay? But, what I'm going to be thinking about is I want to think about each edge as sort of like a pipe with width equal to that capacity. Okay? And I want to send as much kind of water from S to T as possible through those pipes. Okay? So, I wish I hadn't. Okay. So, let's say that this is a graph where everything has a unit capacity, and every time there's some kind of branch point in the edges, that's a node. Okay. So, I can send, say, 1 unit of flow along this first edge. And I'm allowed to split the flow, so maybe I'll send 0.5 along the top, 0.5 down below, okay? And the rules I have to obey is the amount of water I send on an edge is at most the capacity of the edge. So in that picture, everything is unit capacity, so I can only send at most 1. The other rule is that except for S and T, what goes in has to go out. So think of water as coming out of the source S and leaving the system as sink T. Otherwise, what goes into a vertex for the other vertices has to equal the amount going out. Okay, so this is called conservation of flow. All right, so continuing on, maybe I'll send 1 unit of flow along the bottom. Maybe I'll split it up for fun, 0.5 on top, 0.5 on the bottom. Now, if I look at this junction point in the middle, okay, I now have 1 unit of flow going into that vertex. So 1 unit of flow has to go out. Maybe 1 like that. And then at this point, I'm welcome to split it up again. So maybe I'll send 0.5 there, 0.5 there. Again, at this junction point, we now have 1 unit of flow going in, so 1 unit of flow has to go out. Okay? So this would be, sending 2 units of flow from S to T. Okay? Okay, that's right. Okay, so conservation of flow. Capacity constraints we're used to. Conservation of flow is maybe the new thing. And so we're saying that the amount of flow that goes in would be 3 units there, 5 units there, has to be equal to the amount of flow, the total amount of flow going out for every vertex except for those endpoints. Okay, so now, because of conservation of flow, because what goes in is what goes out at every non-terminal vertex, the total amount that leaves S has to always equal the total amount that kind of goes into T and gets sucked out of the system. We can do some sums and double check, but I think this should make sense. Yeah?
Wait, why is it only for the non-terminal versus?
Oh, those are just the rules of the game. Yeah, so my goal, yes, so the rules of the game are, I'm constrained, and I insist that we conserve flow at all the non-terminal vertices. We're going to connect this very closely to all the past stuff we've been discussing in just a moment, and then it'll be even clearer. So, as long as I'm obeying conservation of flow, then the flow, all the flow that leaves S, that S puts into the system, can only leave the system at T. All the other vertices it has to just pass through. So the amount of flow, sort of net flow going out of S, is always a net flow going into T. Okay. So this quantity, this common quantity, we'll refer to as the size of the flow. Now, it doesn't have to be water. It could be internet traffic. It could be electricity. It could be lots of things. Okay? But it's some kind of infinitely divisible quantity. Okay? So the problem we're going to be concerned with is trying to find the S to T flow of maximum size. I want to push out as much water as possible to T. Okay? All right. Okay, so now let me relate this to one more comment. So the problem we've been discussing last week, or up to this point, packing path, removing edges is very combinatorial. It feels like spanning trees, right? I'm packing paths, I'm removing edges, right? It's like shortest paths and all these graph problems we did. What's interesting about the max flow problem is that although there's a very natural interpretation in the graph, at some level it's just like a totally mathematical problem, where I'm just trying to choose a vector. Okay, that vector is sort of keeping track of how much flow I'm running on each edge. Okay. And all the constraints of my system are easy to express mathematically. Okay, so let me highlight some points. Okay, so I want to choose some vector f. Okay. My constraints are, f has to be at most a capacity on every edge. Okay. And then the conservation of flow, what goes in, what goes out, can be seen as an equality. So here I'm summing over all the edges going into a vertex V, the amount of flow going in, and it has to be equal to the total flow going out of V for every vertex V except for S and T. Okay. And up here, I am describing, did I get it backwards? No, that's okay. So this here is summing up the amount of flow that's leaving S And then there's no reason to push flow into S, but just in case. Okay, so that difference, the objective I'm trying to maximize is describing the size of the flow. The total amount of flow that S is putting into the system. So there's no reason why writing down the mathematics would yield much intuition. But I think it's what I'm partly want to do. We won't talk about linear programs too much in this class, but they are actually very important and very central to computer science. So I'm going to be using max flow as sort of our working model, an example of a linear program. And some of the things we learn about max flow extend more generally. It gets more technical to discuss kind of linear programs as purely an abstraction. But many of the morals do apply, and I want us to be aware of this. So the point is that it's sort of like a mathematical program that's in mathematical terms very simple to express. Equalities, inequalities. Linear systems are very nice for computers. There's no quadratics, there's no exponents, there's no sine or cosine. Everything is linear. And one thing that you should know as a fact, none of the algorithms are particularly easy to prove or analyze, is that any linear program can be solved in polynomial time. So take whatever problem you're working on, if you can express it as sort of a bunch of linear constraints, you already have an algorithm. Max flow would just be one example. Okay. I'll also point out that a lot of people write linear program software. They're considered pretty reliable in practice. Now, one maybe limitation from our point of view, max flow is nice because it's natural to say, I want 3 units of flow, 0.5 units of flow. It's naturally continuous and fractional problem. But other problems like spanning tree or shortest path, they feel more discrete. I take an edge, I don't take an edge, stuff like that. Okay. What good are linear programs there? Many people will still take their discrete problem and sort of write down the problem except allow the variables, instead of being 0 or 1, to be continuous. Okay. And they'll just solve it. They'll put in the linear program solver, see what the fractional values come out to, and try to use those values as a hint towards solving the original discrete problem. So the linear program tells you to take, 0.9 of that edge or something. You might round that up to, okay, I should take that edge. Okay, so there's this whole playbook of taking mysterious problem A, discrete problem A, writing down the linear program for it, just putting it into the black box, and trying to use that as a hint to solve the original discrete problem. Okay? That's roughly, I think, all I'll say about linear programs in this lecture. Okay. Now let's relate max flow to everything that we discussed, in particular to path packings and to the minimum cut problem. The pictures clearly are looking pretty similar, and the input is the same. We have S and T in capacities. So what's going on? Okay, so let's compare path packings to flow. So let's let X be some kind of feasible path packing. Could be a maximum one. Now I claim that you can call it with a flow of the same size, same total quantity as your path packing. What would that flow be? So I want to assign values to all the edges. You're given a weighted combination of paths. Okay, so one interpretation is to think of each path going from S to T as like one particular unit of flow going a particular path or something. Okay, that's not actually how liquid will actually intermix and stuff like that. But that analogy would suggest, okay, let me define the flow on an edge E to be, let me sum up over all the paths P that contain the edge, the total amount of that path I took. Okay, so here's S and T, and here's a particular edge E, right? And there's all these paths that use E. Okay, so there I've drawn two paths that use E, and I might set the flow to be equal to 2 or something, because I've used two paths. Use that edge for two paths. Okay. So what's really nice? Okay, so we have two constraints, right? We have these capacity constraints, and also this what goes in is what goes out constraints. Okay. Now, I'm saying that the flow on an edge is equal to the total quantity of paths that used it, which was required to be at most the capacity of the edge. So we obey the capacities. Okay. And then what's really great for the conservation constraints, if I'm looking at a particular vertex, right, and I'm taking the path and I'm thinking of it as flow, but every path that goes through V also leaves V because it has to go to T. Okay. So when I turn all those paths into flow, I always maintain this fact that the flow that goes in is equal to the flow that goes out. Okay? Because paths can't stop except at T. Okay? So that gives us that whatever is the maximum number of paths I can take, I can always convert it into a flow of the same size. So the max flow is always the maximum number of paths I can take, or maximum quantity of paths that I can take. Okay. Now, okay, what about the minimum cut as compared to the maximum flow? Okay. So let's say that the minimum ST cut maybe is induced by this set of vertices around S, so it's all the edges that leave S. Okay. And there's some flow from S to T. Okay. Now, all the flow starts at S and ends in T. Okay. Okay, so the net flow leaving my set A is in red, okay, is at most the total capacity of the edges leaving A. Because it can only leave the set using the edges from A. Okay. All right, maybe not so compelling. But the consequence is that the size of the flow, the total amount of liquid I'm sending from S to T, is also constrained by the capacity of that S to T cut. All right, so what that gives us is that the max flow is at most the min cut. Okay. So what have we shown? So we understand this path packing and cut problem pretty well. And we're introducing this flow problem. And it's always sandwiched in between these two values. Okay, so for any path packing, I can find a flow of the same value. On the other hand, the flow going from S to T is still constrained by the S to T cuts. But we already know that these opposite values are equal. Okay. So in fact, everything is equal. So let's see, did I have it set up? Yeah. The max flow is actually equal to the maximum size of any path packing, and it's equal to the minimum size of any SC cut, minimum capacity. That's not obvious. I mean, at some level, you might have wondered if sort of not having to maintain the actual pass and just worry about pushing liquid, whether that would allow you to kind of push more than you can get from a path packing, and this is saying no. Okay, so we now have three problems that are roughly equivalent. I'm also going to briefly mention that in the PSO, you'll do the opposite direction of this, where you'll take a flow from S to T and then find a path packing that sort of matches it. We know that there always is a path packing of the same value, but we'll come up with a very fast algorithm to give this decomposition of paths. Is sometimes called the flow decomposition. Okay. All right. Okay, so having established that max flow is really more or less the same problem as max path packing and minimum ST cut. Let's talk about trying to get polynomial time algorithms for max flow and simultaneously the path packing problem and the min cut problem. Okay. So in developing an algorithm for flow, it's helpful to sort of extend our notion of residual graphs to flow. Okay? And it's going to be exactly what you expect. So if I have, on the left some graphs as capacities, and I'm routing 1 unit of flow along the middle path in yellow. Okay? Then at some level, I should, in the integer case, I would add 1 reverse edge for each of those. And that should map to sort of an edge in the opposite direction with that add capacity. Yeah?
If you reverse the edges like that, would there be a cycle where you go like from S and then you go down to the right and then up and then down to the left and back to S and then you just keep doing that?
Okay, so on the right there's a cycle. There's a triangle. And your goal, okay, this is a good question. So why can't I just keep taking tons of that triangle, and maybe one, and then you probably go back and forth along that triangle or something. But we're only interested in the net flow leaving S. So if I kind of, so to speak, take a triangle, I'm sending 1 unit of flow out of S, and then sending 1 unit of flow back in. So the net flow going out of S is the same. I'm really trying to send as much flow as possible from S to T. Yeah, so that's why in the objective I've subtracted out the amount of flow going into S as well. So that you can't do this kind of pumping S back into itself and getting free points. Okay. Alright, so let me define this a little more slowly. If I have a flow, and I'm looking at a particular edge, with capacity CE, and let's say that out of CE units of flow, I'm currently sending, I guess F of E would be the notation. Okay. Then in the residual graph, I sort of have, I got this backwards. I have 10 units of capacity, I'm sending 5 units of flow. That leaves 10 minus 5 is equal to 5 units of capacity in the forwards direction. Okay? And then the equivalent quantity of the opposite, okay, would be Fe. Okay? Now using the fake edge in the opposite direction is sort of like pushing back the liquid, sort of decreasing the net flow on the edge. Alright. So that's fine. So if I can take our algorithm from last time, and instead of trying to get the maximum number of edge disjoint paths, maybe I just want to get the maximum ST flow. Okay. And, before we used to remove all the edges from the graph and add the reverse. Now, kind of more generically, I'm going to sort of update the residual graph. Okay, so some capacities go down and the opposite capacities go up. Okay, now it's just sort of a subtraction and addition. Okay. Now, one thing that I'm allowed to do, and maybe instead of taking the path P, I want to push flow along P. Okay, so if I find this path, right, I might push water and increase all the values of the vector. Okay. Now, one degree of freedom that we didn't have when talking about edge disjoint paths is that I can decide how much kind of flow to route and how big of an update to make. Before it was natural just to take a path and do an update, but now we're kind of manipulating quantities. What would be one choice is, what would be a choice? How am I to determine how much flow to send along a path I found? Yeah.
Whatever like the minimum capacity edges and that much.
Yeah, so at some level, let's send as much as possible. Yeah. Which would amount to whatever path I took, checking all the capacities along the path, and identifying the minimum one, maybe it's 0.3, and sending 0.3 units of flow. That's natural. Okay, so this is reasonable, but it's not necessarily polynomial time. We sort of had this example, I think this came up. But here's sort of an extreme example. But if I, send 1 unit of flow, or if I choose this path, I can only send 1 unit of flow. Okay? And so what would happen is that I would now get the opposite direction of the edge with 1 capacity. And then I would send 1 more unit of flow, like this. And so if we're not clever about how we choose our paths, I'm only sending 1 unit of flow each time and gradually updating the capacities. And in this case, we'll need 2 to the 100, I guess, iterations. Okay, so these bottleneck edges can be an issue. Okay. But the general algorithmic framework makes sense. Let's find a path and send as much flow as possible. Okay. All right. So, okay. All right, so here's one last chance to open up the floor. That is, what are some ideas to take this framework of choosing path, sending flow, and trying to do something different or more clever within the framework that might help us? The current framework is to just find a path in a residual graph and send as much flow as possible. It's not necessarily work, but we're going to come up with a more specific version of that algorithm. Any crazy ideas? All right, I'll mention two. One, that was suggested last class, is to always select the shortest path. Okay. A second one, at some level, okay, what's the issue? Is this example, I'm using that edge of capacity 1, that's a bad idea. Okay. So maybe we can try to maximize this bottleneck edge. Okay. So try to find paths where all the capacities are big. So I can set a more flow in each iteration. I think those are both natural. So today, or now, we'll discuss this algorithm. Okay. And then the homework lays out the steps for this one. Okay. And they're going to get slightly different styles of running time. Okay. All right, so this is going to give us sort of the cleaner analysis. All right, so here's the algorithm. As long as there's a path from S to T, I'm going to find the shortest one and route as much flow as possible. All right, so we have a little time left to analyze this thing. Okay. All right, so there's the algorithm in the yellow box. It's very natural, given our last Thursday's discussion. Find the shortest path from S to T, send as much flow as possible, update the residual graph, repeat until there's no path left. I don't have to worry really about correctness, because it's really kind of following the same Ford-Fulkerson framework from before, the exact same proof. We'll get you there. Okay. But the key is, how am I going to argue that this thing has a polynomial running time? It might seem like a natural heuristic, but it's not at all obvious how to prove it works. So it turns out that the key idea is to focus in on the distances in the residual graph. Okay? So I should have maybe made this more specific. When I say shortest path, I'm just going to count the number of edges. I'm just going to do BFS. Okay. So we are going to show that as I continue to augment along the shortest path from S to V, for any particular V, the distance from S to V in the residual graph does not go down. Okay. This is what we're going to show. As long as I keep choosing the shortest path left, I'll actually somehow guarantee that all the vertices are gradually getting further and further away from V. Alright, so let me first explain why this is useful. So let's just assume this to be true. That this algorithm has this property that the distances from the source in the residual graph are monotonically increasing. Okay. And with that assumption, now let's look at a particular edge, E, with I guess endpoints U and V. Okay? And we're going to study what's going on with these distance labels. Okay, so this is distance labels in the breadth first search sense. So you can think of each of these purple contour lines as one breadth first search layer. Okay. Alright, so now as we run the algorithm, sometimes I use up all the capacity in E, and it gets removed from the residual graph in the sense that its capacity is 0. Okay, when its capacity is 0, we remove it. And sometimes, when I push flow in the opposite direction, E gets reintroduced into the graph. now has positive capacity. Okay, so over time, E is appearing and disappearing. So what's going on? Let's look at a point in time when E is removed. Right? So, okay, what does that mean? That means that E appeared in the shortest S to T path, and it was the bottleneck edge. Because I pushed as most flow as possible, and he used up all the capacity in E. But just knowing that they were in the shortest path, that this edge was in the shortest path, I know that level V, the BFS layer, is exactly 1 after U. So every time E disappears from the graph, that means it had just appeared in the shortest S to T path. So for at least a split instance, I had this fact. Level indicates distance. Okay. Now, what happens when it reappears in the residual graph? Okay. It only reappears in a residual graph when previously I just sent flow in the opposite direction, which gave it more capacity. It went from capacity 0 to something positive. So the opposite direction had just appeared in the shortest S to T path. So that means in that right before E reappeared and the opposite edge appeared in the shortest S to T path, I knew that V was 1 layer closer than V. What did I say? V was 1 layer closer than U. So what's going on? Because I'm only augmenting along S to T paths, I'm starting to use these distance labels as extra info in my proof. Okay, and actually, I know something about the distance labels whenever an edge is removed from the residual graph, or whenever an edge is reintroduced into the residual graph, because that means either it or the opposite edge was participating in the shortest S to T path. Okay. All right, so what happens when we combine these things? That means that, I delete an edge and it comes back. Okay. So initially U was closer to S than V, but later when it came back, V was closer to S than U. Okay. Now the only issue is, but these hands could be anywhere, except that key lemma says the distances never go down. So when it switched over, U did not go down or anything, so V definitely went up. V did not go down, so U did. Okay, so if I know that these only go up over time, and that they switch roles, right, then I know that at least one of them has gone up at least one distance label. All right, so now what's the maximum distance I can have from S? It could be infinity, but among the finite ones. What's the maximum number of edges in a path? Yeah.
The total number of edges.
Yeah, it could be M, or because it's a path, even number of vertices, -1. Okay, so U can only be at most n minus 1 hops away. V can only be at most n minus 1 hops away. So whenever an edge gets deleted and added, you know that there's some progress being made. Okay? So that tells me that, a particular edge can only get added and deleted at most, n times or something. Okay, because I can charge it to the distance labels going up of the endpoints. Okay, now the last observation is going to use the fact that in my algorithm, I'm sending as much flow as possible along the S to T path. So in particular, whatever edge kind of constrains the amount as much as possible is getting deleted from the graph. Right? So every iteration removes one edge from the residual graph. So if I know that every iteration removes at least one edge, and I know that edges can only get removed n times each, how many iterations can I have? Okay, so I'm going to charge every iteration to removing some edge. Each edge can only get removed n times. That matches. So somehow, assuming that the labels never go down, they can only go up, we can actually argue that augmenting as much as possible along the shortest S to T path is guaranteed to have a polynomial number of iterations. It's sort of a very funny proof because this proof doesn't even keep track of how much flow I've sent. Nowhere in here did I say, oh, I've already sent half the flow, 3/4 the total flow. Progress is entirely measured by the distances from S in the residual graph. There's a dual interpretation of this, but that's what's so kind of interesting about it. Okay, so as far as the overall running time goes, each iteration I just run breadth first search to find the shortest path from S to T. We argued that there's only mn iterations. So the running time is m squared n. Okay. All right, good. Okay, so then what's left is proving this key lemma that as long as I'm augmenting along the shortest path from S to T, the distances never go down. Okay, that was important to ensure that when things do switch over, some progress was made. Okay, so, for every vertex, the distance from S to V in the residual graph never decreases. Okay. Alright, so let's fix V. Okay, and suppose we augment along some shortest path from S to T. Actually, we're not fixing V. I want to show that none of the levels decrease. Okay, and I'm going to prove this by induction on the level of the vertex before augmenting. Okay. So, I think that, in the base case, level 0 is just S. That's the only vertex we can get to in 0 edges. So that never goes down. S can always get to S and 0 edges. Okay. So let's look at the greater level. So I'm looking at a vertex V at level 10 or level 9, some level that's greater than 0. Okay. So I'm going to let alpha denote the level before and beta denote the level after. I want to show that beta is greater than or equal to alpha. Okay. This is really uncomfortable. And so suppose by contradiction that beta is less than alpha. Okay. All right, so, let's look at the shortest path from S to V. Okay. Then, And let's let U be the vertex that came before it in that shortest S to V path. So, okay, so that means that before, okay, how would I put this? Okay, so this is, okay, so this was level alpha before, right? And so this is alpha minus 1. Okay. So I know that U was at level alpha minus 1 before. And I've already assuming the claim for alpha minus 1. So by induction on levels. Okay. I know that, oh, I'm sorry, I messed this up. Okay. Okay. Let's just get this. Okay. Okay, so I know that okay, I think we're actually doing induction on beta. Okay, so the level of U is equal to beta minus 1 just after by choice of U. So I'm actually looking at the shortest path from S to V after the augmentation. Okay? And so by induction on beta, I know that whatever level U was at before the augmentation was less than equal to beta minus 1. Okay, sorry about the typo. Okay, so all right, so if by contradiction, I'm assuming that the level of V before augmentation is bigger than alpha, then it must be the case that the edge U to V was not in the graph before. Because this represents a hop of size greater than equal to, it's more than at least two layers in between them. Okay, so that means that edge V to U was in the previous augmenting path because I added the backwards edge. Okay. And that means that the level of V was less than the level of U before the augmentation. But that would take V and put it somewhere over here instead. And there we get our contradiction. Alright, so sorry for stuttering. If this had been that, I wouldn't have stumbled. So I'm sorry about that. Okay. Alright, so in any case, hopefully you believe me. Okay, so let me just sum up what we did. So we're trying to look at this max flow problem where you may be sending tons of flow. Right? Just the exponentially large flow is tons of capacity, real value capacities, whatever. And the algorithm we settled upon is always choosing the shortest path from S to T and sending as much flow as possible at some level that feels natural. Find the shortest pipes. Okay. What I find so interesting about this proof is that we never measured how much flow had already been sent. The proof was completely unconcerned. It only focused on what are the distance labels in the residual graph, which is really has to do with the dual min-cut problem, but it's a little harder to explain. But just focusing on those distance labels, okay, and showing that they actually go up over time, and that's how we measure our progress. So S is always at level 0, and gradually the vertices are going farther and farther away, and I have to route along longer and longer paths from S to T. Okay? And that's actually how we measure progress in the algorithm, by measuring the distance label. So it's much less, I think most of the other algorithms we've done, it was very clear how we're approaching determination, but this is unclear. It's not obvious that the algorithm's making progress. You can't really tell by, say, how much flow you've already routed. You can only look at the distances increasing in the residual graph. Okay, it was a little bit more of a delicate analysis, but the conclusion is that we do have a strongly polynomial time running time. This doesn't even depend on, say, log of lambda or anything like that. The other algorithm will give you log of lambda, as you'll find out. Okay, so we get this very clean m squared n running time. I'll only end with one closing historical note. This is from 1967. So before this paper appeared, the existing algorithm was Ford-Fulkerson, was augmenting path, and at some level, there wasn't a strong distinction made between polynomial time algorithms and just algorithms. So m times lambda was kind of considered satisfactory. It worked. It ran on vacuum tubes or whatever. So people are happy. So, CARP is the same CARP that did the P versus NP paper. Edmonds is also a highly significant figure in common core optimization. So they went in and they said, no, I really want a polynomial time algorithm at a time when people weren't fully convinced that polynomial time algorithms were important. Okay, so they did that for this problem, where they give a strongly polynomial time algorithm. At some level, it's within the framework of Ford-Fulkerson. They ran for 2 pages about why it's important. Okay, and so this is also a very important paper historically, in terms of really, and then P versus NP comes 5 years later and really puts the final nail in the coffin. But this was a very important early paper in terms of arguing about the importance of establishing strongly polynomial running time. Question?
You just go back to the last page with the last simple proof.
Okay. And hopefully the notes will never have any typos in it to begin with. Okay. All right. That's it. Next time we'll do applications of mass flow, which is really fun.